All right, let's go through. We're going to talk about composite functions today. Composite functions, these are kind of cool. Basically, imagine that you have a pencil factory. Okay, we've got a pencil factory. And we're making pencils. But to make pencils, you basically got two factories going on. Basically, you've got a wood factory to make the shaft, and then a lead factory for the graphite part, you know, the actual tip of the pencil. And so what you do is you put, so I guess logs or something like that. You got logs, they go into your wood factory. So logs are going into your wood factory, and they come out as basically the shaft part of the pencil. Number two. Why are they number two pencils? That's a good question. Why is it number one? Really? Oh, okay. I didn't know that. All right. So we got number two, and then it goes into the lead part, and you get the lead out, or whatever they put in there. And boom, you have a full number two pencil. All right. Note this process. When I plugged it into the wood factory, I got out the shaft part. And then I took the output from that wood factory and put it in to the other factory. And then I got something out. Y'all see where I'm going with this? All right. Some of you are like, yes. Some of you are like, not at all. Suppose I had two functions. Let's say we had f of x is equal to, I don't know, x plus 5. And let's say g of x is equal to negative x minus 6. I'll wait for you to put it down so we can kind of have this idea. What if I want f of, so this little 0 with the like kind of like hole in it, whatever, means f of g of x, which also could be written f and then g of x on the inside of that, meaning the same thing. In other words, what I'm saying is g of x is my inner function and f of x is my outer function. Okay, so what's going to happen? Or actually, let's do another something a little different. Instead of f of g of x, let's do f of g of 2. So let's think about what in the world does this mean? This means that my g of x function is my first function. In other words, I'm going to put 2 into my g of x function. Whatever I get out of that, I will then put into my outer function, f of x, and get something out, and that'll be the answer. Does that kind of make sense? So let's do it. So g of 2, when I plug 2 into my function, I get negative 8 as an output. Does that make sense so far? And then I'm going to take that negative 8 and do what with it? Plug it into f. The answer is negative 3. So what I can say is f of g of 2 is negative 3. Does that make sense? You take the input, plug it into one function, take that output, plug it into the other function. Questions? All right. You got 10 minutes. Good luck. About 5. See as far as you can get. If you don't get through all of them, that is fine. I want you to try first. how did I miss? Oh, there we go. All right. We want to find the composite function and its domain. All right. So we've done some problems, but now we're going to actually find the functions themselves. So kind of similar idea here. We're going to take g of x, but this time we're going to take the whole thing and plug it into where x was. Does that kind of make sense? So you're going to take your entire inner function now and plug in where f was. So in this case, you'd have f of x squared plus 9, which basically would be x squared plus 9 squared. In other words, wherever x was, we have now taken the entire inner function and stuffed it in there. It's almost like if you go back to our analogy of a factory, it's like if you consolidated a factory. Instead of having one factory somewhere else and shipping that stuff to you and then doing something else, we said, hey, we'll just put the two factories together. And that's what this does. If you have f of g of x, you're just taking your g of x factory and putting it into your f of x factory. Does that kind of make sense? So f of g, or g of f of x, once again, now this is the inner function. So we're going to take that and plug that in here. So you can see how it's a little different because of g of x squared, you'd have x squared plus 9. Once again, it's different because you're taking now f and plugging into g, as opposed to g plugging into x or f. What's inner and what's outer matters. All right, so let's talk about the domain. The domain for both of these is negative infinity to positive infinity, because obviously I have no restrictions on anything, right? I mean, think about it. There are no like square roots I have to deal with, no rationals that I have to deal with, right? Because those are the two, like if I have to deal with the denominator or if I have to deal with the square root, those are the main things that will stop me from having domain being negative infinity to positive infinity, but I don't have anything like that in this case. Everybody cool with that? All right, let's do f of f. F of f, these are fun. Basically, you're going to take f and plug it into itself. So this would be x squared squared. And of course, you can clean these up. Like this could be x to the fourth. If you really wanted to, you could multiply this out. You'd have what, x to the fourth plus 18x squared plus 81. But, or and then you could say this right here to be x to the fourth plus 9. Like I could clean them up, but it's not really going to make too much. All right, let's do g of g. G of g, we're going to take our g function and plug it into itself. So we're basically doing g of x squared plus 9. So once again, wherever x was, we are now replacing it with x squared plus 9. Whenever you replace something, guys, make sure that you're kind of putting a parentheses around it. So you see I'm replacing x. So I'm putting a parentheses around where it's been replaced. Does everybody kind of see that? And if I was, I could say, okay, this is really x to the fourth plus 18x squared plus 81 plus 9, or x to the fourth plus 18x squared plus 90. And if you're not 100% sure about this, just flow it out. X squared plus 9 times x squared plus 9, just flow it out. But I promise you this. Questions on that? All right, we're rolling along. We're making pretty good time here. All right, finding the components of a composite function. Find functions f and g such that f of g is equal to x plus 1 to the 50th. All right, so I'm gonna give you a couple of minutes for that one. Think if you can come up with functions f, what should f be? What should g be? So that f of g would be x squared plus 1 to the 50th. There's an infinite amount of answers, but I will give you a minute to think about it. One that kind of sticks out. Or at least I think. As a matter of fact, let me blow this up because I feel like y'all can really see it. Once again, doesn't have to be too fancy. This is exactly what I was thinking of. But of course, there are infinite amount of combinations of these two, right? Because you could have x squared plus 1 squared, but then f of x would have to be x to the 25th. So that you get to that 50, 2 times 25 being 50. You could do a whole bunch of other things you wanted to, but like this one I think will definitely suffice. Did you all get something similar, or did you do something a little different, or are you completely confused altogether? All right, I'm gonna do a quick check. Put 5 fingers in the air if you're like, I completely understand this. 3 if you're middling, and 1 if you're completely lost. All right, real quick. Awesome. Not all the way up, like it, like in front of your chest, so like you can kind of like move your shoulder around, make sure nobody's like, you be like, so you don't have to embarrass yourself. You'd be like, 1. I'll do that from time to time, and hopefully, like when we take our breaks and stuff like that, I can kind of help anybody who's a little lost. All right, let's talk about one-to-one for a second. If a function is one-to-one, that means that for every input has a distinct output, every output has a distinct input. All right, so an example of a one-to-one function is this one. Everything in the domain has only one answer in the range. This is the example of something that's not one-to-one. It's a function, sure, because inputs don't go to 2 outputs, but you can see that these 2 inputs actually go to this output, so it's not one-to-one. And then not a function just means that, of course, you got an input that gives you 2 outputs. So remember, it kind of something like that. So let's talk about determining whether the following are one-to-one. So we're on part 4, problem 4. So what we can say is, okay, I've got 4. When I input 4, I get out 6. Okay, that works. If I input 3, I get out 9. Okay. If I input 8, I get out 3. If I input 6, I get out 5. So is this one-to-one? Yes. This is one-to-one because for every input is a distinct output, period. All right, now let's take a look at part B, which kind of like I give it away in a way. So for 3, get out 5. For -2, I get out 7. For -8, I get out 5. For 6, I get out -3. Is this one-to-one? No. Is it a function? Yes, it's still a function, right? Because there are no inputs that you see twice. Like, for example, you don't see anything like 3, 8 when you've already seen 3, 5, right? So it's still a function, but it's not a one-to-one function because of, well, it's underlined, right? You got two inputs mapped to the output file. All right, y equals x to the 4th. Is this a one-to-one function? Think about it. Would this be a one-to-one function? And while you're thinking about it, I'm just going to plug a couple of numbers in. Is this a one-to-one function? In other words, for every input, there's only one distinct output. I see people shaking their heads, but somebody needs to speak up. Is this one-to-one function? Yes or no? No. If I plug one in, I get out 1. If I plug -1 in, I also get out 1. Can this be one-to-one? Now, once again, guys, if I ask you a question and you shout out the wrong answer, that's good. That means you're paying attention. You know what I'm saying? And so what I want you guys to do is like, please get over this fear of getting something wrong. I'd rather you get it wrong in here where we can help you kind of get over the hump as opposed to getting it wrong on a test. Wouldn't you agree? So don't be afraid of being wrong, just be wrong and we'll fix it. All right, the last thing I want to say before we take our break is we're going to talk about the horizontal line test. If every horizontal line intersects the graph at only one point, F, the function is 1, 2, 1. In other words, remember we have the vertical line test tells us whether something's a function or not. Remember that? Right? If we draw vertical lines and we hit something twice, it's not a function. For example, if you have something kind of like this, x equals y squared, this obviously is not a function because it doesn't pass the vertical line test. I can draw a vertical line and hit something twice. But in addition to the vertical line test, the horizontal line test lets us know whether something is 1 to 1. So in other words, if we look at this, so number 5, for the following functions, determine whether the function is 1 to 1. In this case, I can draw as many vertical lines as I want to. I'll never hit 2 points at once. So this is 1 to 1. But if I draw a horizontal line here, I hit my function twice. So this is not 1 to 1. They're both functions, right? They both pass the vertical line test, but one of them does not pass the horizontal line test. Questions? Now we want to talk about inverse functions, all right? These are functions that undo the function that we want. Also, we can think about them as an inverse simply is where x and y switch places. So if we go to Desmos, we think about it. Let's say we have y equals like 5x plus 9. So we got y equals 5x plus 9. And if we create this thing right here, which actually, let's do y equals 5x plus 1 or something like that. Let's make this a little bit different. Let's make it 2x. All right, cool. All right, so we got y is equal to 2x plus 1, which you can see if I blow this up, which, how do you blow this thing up? You can see the table has these values here, okay? Now, what if I change the y and x values? Instead of saying y equals 2x plus 1, I say that x equals 2y plus 1. Okay. And if I solve for y, I would get that y equals, let's see, x plus 1 over 2. You can see like x minus 1 over 2. All right. So you see these two are the same thing, right? All right, so what does that have to do with anything? Let's take a look at their tables. For y equals 2x plus 1, you get -2, -3, -1, -1, 0, 1, 1, 3, and so on and so forth. But if I take these values, -3, -1, 1, 3, and 5, what do you notice about the x and y columns between these two? What do you notice about those? they're switched. Does that make sense? So these two functions are what we call inverses of each other. 2x plus 1 is the inverse of x minus 1 over 2. Why? Because the x column and y columns have switched places. Does that make sense? So at the heart of an inverse, that's what we're doing. Another interesting thing about inverses is graphically, they are reflected over the y equals x line. Y'all see how graphically they're reflected over the y equals x line? And so you can see it pretty clearly, at least as in Desmos, that they're reflected. Another great thing inverses do is they undo the function that you're doing. So it's like multiplication to division are inverses of each other because one will undo the other. All right, so let's take a look at 6, and I want everybody to work on this one together. Find the function of the one-to-one, find the inverse of this one-to-one function. Oh, and by the way, note, if it's a pure inverse, then it has to be the inverse of a one-to-one function. State the domain and range of the inverse function. So let's think about it. If we have -6, -13, -5, -15, -4, 7, -3, 14, and -2, 11, then the inverse function, and the way we note the inverse function, so if this is f of x is equal to this, then the inverse function, which we denote with f to the -1, that's just the symbol for inverse. The inverse function would be, well, -13, -6, -15, -5. This is problem 6, by the way, if you're trying to keep up. 7, -4, 14, -3, and 11, -2. What am I doing here? I'm just switching the x's and y's. So if I were to ask you, well, what's the domain of the f of x? Well, the domain of f of x would be the set -6, -5, -4, -3, -2. And the range of f of x, remember, range is your set of outputs, would be, let's see, -13, -15, 7, 14, and 11. However, for f inverse, what would the domain be? -13, -15, 7, 14, and 11. Does that look familiar? Well, it should. It's the range of f. So what can we guess the range of f inverse would be? Right, the domain of f. So in other words, once again, x and y are flip-flopping, right? So your inputs and outputs are switching. So now the range of f inverse would be the domain of f, which would be -6, -5, -4, -3. So they flip-flop. Does that kind of make sense? Ish. All right. Now let's verify that an inverse is a function. This is why we did composite functions first. If two functions are inverses, so we can write this down. If f and g are inverses, then f of g of x is equal to x. Why? Because f and g will do what to each other? Think about it. Yes, that's absolutely correct. Think about it. We said multiplication and division are the easiest inverses, right? Because they cancel each other out. Addition and subtraction cancel each other out, right? So if I have two functions and I claim, hey, these are inverses of each other, that must mean that they cancel each other out. So you'll be left with just x. And of course, we could say g of f of x should also be x. Everything should cancel, you'll be left with your original number. So let's do it. And actually, I'm going to do one kind of thing before this and we'll go from there. So let's do f of 2, for example. So I do f of 2, I'd get 3 times 2 plus 6. That gives me 6 plus 6, which is 12. I'm going to do this kind of fast. So g of 12 would be 1/3, 12 minus 6, 1/3 of 6, which is 2. Note what I started with. Y'all see that? Does that kind of make sense? Your inverse will undo what your function did. So now we can actually prove this. So this was just an example. Now we want to actually show it. So what we can do is we can say, okay, f of g of x, let's think about it. You're going to take your g function and stick it into where x was. So you'll have 3 times 1/3 x minus 6 plus 6. What is the 3 and the 1/3? What are those going to do? Cancel, so you'll end up with x minus 6 plus 6. And then what's the 6 and the 6 going to do? Oh, look, it's x. And thus we could do it the other way around. G of f of x. Well, that's going to be, let's see, 1/3 times 3x plus 6 minus 6, basically. And so 3x plus 6 minus 6, they'll cancel. So 1/3 of 3x, which is 1/3 and 3 will cancel, you're left with x. So good news for us. Now, if we graph these inverses into Desmos, what we should see is they reflect over that line we talked about. So for the 2 that we had, 1/3, and then let's see, x minus 6, I think. Running out of time. And then it was 3x plus 6. You can see that these two lines reflect over y equals x. All right, then. Let's get that. All right, so how do we find the inverse? That's the question. It's 3 main steps. 1, you want to make sure that you've got y and x will switch places. 2, we're going to solve and then check the result. And we're going to go through how to do that with problem 8. So on problem 8, go ahead and write it down. We're given that f of x is equal to x cubed minus 2. So to find its inverse, the first thing I'm going to say is y equals x cubed minus 2. Remember, they mean basically the same thing. So now, if I want an inverse, what are switching? What's switching? X and y. So I'm literally going to do that. I'm going to go ahead and switch x and y. So I'm going to put this in green. So I'm going to have y equals, oops, other way around, right? Now I have x equals y cubed minus 2, which then would give me x plus 2 is equal to y cubed, which how do I get rid of this y cubed? It's going to be kind of ugly, but we're going to have to use the cube root of y to get rid of it on both sides. So basically, if you can think about it, you want to make sure that y equals something. You switch. And then from there, solve for y. We're not done yet. We're going to take this y and we're going to call this f inverse. And that's how it works. Now we can check and make sure that these are indeed inverses of each other by just plugging them in. So if I do f of f inverse, or what I think f inverse is at least, let's see. So if I plug that in, I'd have f of the cube root of x plus 2, which means I'd have the cube root of x plus 2 cubed minus 2. Once again, plugging f inverse into f. What's going to happen with these cube root and cubes? What are they going to do to each other? Cancel. So you'll have with x plus 2 minus 2, which is x, which is exactly what we expected. And I can go the other way around. So f inverse of f, which is x cubed minus 2, would be the cube root of x cubed minus 2 plus 2. Well, the plus 2 and minus 2, they're going to cancel. So you're left with the cube root of x cubed, which is just x again. Exactly what we expected. Questions on that? Just take it from me. Just take your time with these. You will definitely get it. All right, we got enough time, I think, to just squeak in those last two. All right, so we've got the function f of x is equal to 2x plus 1 over x minus 1. It is 1-to-1. Find its inverse. Find the domain and range of the original function and its inverse. Okay. So same deal. I want everybody to write this one down because this one is a little involved. But same idea. So we've got y equals 2x plus 1, x minus 1. And to find the inverse, which I'm going to put in red, we're going to switch the x values and the y values. I'm going to pause right there because I want to make sure everybody's together. Does this make sense so far? Okay. So now what we're going to do is we're going to multiply y minus 5 on both sides. So you know, with x times y minus 1, I mean, is equal to 2y plus 1. All right. Another way people say cross multiplication, that is kind of what is going on, but I prefer to think about multiplying y minus 1 on both sides. Everybody see on the right side, it'll just cancel, right? And then on the left side, you'll have this. So if I distribute out this x, I'm left with xy minus x is equal to 2y plus 1. I'm going to pause right there. I want to make sure everybody's got it. Now what I want to do, now I'm kind of stalling, so you can go ahead and write it down. Now what I want to do is I want to put all the y's on one side and everything else on the other side. So I'll end up with xy minus 2y equals positive x plus 1. All I've done is subtracted 2y on both sides and added x on both sides. Are y'all with me? Say yes. Yes. Cool. And so now, I'm going to pause right there so you can get that down. Now what I'm going to do is I want to get y by itself still. So I can factor it out of xy and -2. So I can do y, and then we got x minus 2 equal to x plus 1. Everybody cool with that? Just pulling the y out of x, pulling it out of the 2. And can anybody guess what I'll do to finish this problem? Exactly. With y is equal to x plus 1 over x. Or f inverse of x is equal to x Now we could determine the domain and range. But what's kind of interesting here is that the domain of f of x of f inverse is everywhere except for x minus 2, right? So the domain of f inverse would be, you know, negative infinity to 2, union 2 to infinity. And the domain of your original function, which I should probably put in green, I guess, but the domain of your original function would be everywhere except for positive 1. The negative inverse. 1. So here's a trick. If I want the range of my original function, right? I want the range of the original function be the domain of the inverse function. So I can say that the range would be negative infinity to union 2. And I can plug it in decimals to show that it's true, but you get the idea. Everybody see how I kind of use a shortcut on that one? Last problem of the day, guys. Yay. I know, right? The function f of x equals x squared, where x is greater than 0, is 1 to 1. No, we actually have to include this piece where x is greater than 0. Why? Because if you think about the regular x squared function, is this x squared function actually 1 to 1? No, but what if I cut off all this stuff? Is it 1 to 1 now? Yeah. If I cut off everything before 0, or restrict the domain, now this part, if this is left, it's a 1 to 1 function. So sometimes if you want to create something that's 1 to 1, you're going to restrict the domain. So let's find the inverse, because this is actually not that hard to find. So if we have f of x is equal to x squared, we're going to go through our steps. Y is equal to x squared. Then we switch it. X is equal to y squared. And now what are we going to do to solve for y? What do you do for squareds? How do we get rid of squareds? Right. So what we can say is f inverse the square root of x. But note, this is very important. That only works for x is greater than 0 originally. So if we plug it into Desmos, you can see that. So if I have x squared, once again, not a 1 to 1 function, but remember, I restricted the domain to be just where x was greater than or equal to 0. So where x is greater than or equal to 0. And then if I look at the square root of x, you can see indeed these two are inverses as they mirror each other over y equals